Hello, welcome to the second video to accompany the Further Maths Conference Complex Numbers session. In this video, we're going to look at how we work with complex numbers. OK, so how do you think we should add and subtract complex numbers? Well, what we really want to do is to see how many real bits and how many imaginary bits we have. So it's just collecting terms. So here we've got 2 plus 3 is 5, and 5i and minus 8i gives me minus 3i. Subtraction is just the same, but of course you need to take more care. 2 take away 3 is minus 1, and 5i take away minus 8i is 13i. So here's a part of Further Maths which is just Year 7 work on collecting terms. How do you think we should multiply complex numbers? Well, we want complex numbers to obey all the usual rules of algebra. So let's multiply as we do in algebra. So 3 times 4 is 12. 3 times minus I is minus 3i. 2i times 4 is plus 8i. And then 2i times minus I is minus 2i squared. So I squared is minus 1, so this term here is plus 2, plus 12 is 14, and plus 5i. While if you and your students are confident it's perfectly okay to do that step as a single step, I would advise against trying to write that as plus 2 straight away. The opportunity for losing minus signs is just too great. We can generalise, of course, so for a plus bi multiplied by c plus di, we'll get ac plus adi plus bci plus bdi squared. So the real bit, we've got minus bd here, so that's ac minus bd, and then collecting the imaginary parts, ad plus bci. We strongly recommend the box method because it's so useful for polynomial division later. Polynomial division by using the box method backwards is so much easier to learn for weaker students than the traditional long division method, and it leads naturally into a mental method for stronger students, so it's win-win. If they're not familiar with it from lower down the school, make sure you're using it at this stage. And we combine those together as we did before to get 14 plus 5i. And then in general, AC, BCI, ADI, BDI squared, and collecting real and imaginary parts, AC minus BD plus AD plus BCI. And look, here we are again using Year 7 content, albeit slightly extended by remembering that we can reduce I squared to minus 1. Complex conjugates. This is just something we've given a name to because it's a useful idea that we'll refer to and use several times. Let's look again at that quadratic equation that we solved in the first video. What do you notice? Pause the video for a moment while you look back at your working out for this and think about why it should be true. OK, well hopefully the previous slide was a big hint that these two solutions are complex conjugates. If you look back at your working, you'll see that it's this plus minus that gives it. We can split this into two separate parts. This bit is clearly real, and this bit will turn out to be pure imaginary. So you can see that the structure of the quadratic formula shows that this will always be the case. This is a really important result and one that is often implicitly required in exams, so students need to be on top of it. Here are some more things to think about. Pause the video while you work them out, and then try to generalise what you find. OK, you should have got z plus z star is 10, and z times z star is 41. Both of these are real numbers. Is that a coincidence? Let's try a general complex number, z equals a plus bi, to find out. So now we get z plus z star is 2a, and the imaginary parts will always cancel out. And z times z star being the difference of two squares, the I terms cancel out, and we're left with a squared plus b squared. So yes, this always happens. This is the sort of simple reasoning that students should be familiar with from GCSE, but they may not have formalised it. Here you have a good opportunity to develop that formalisation of reasoning within a fairly straightforward context. And now to division. The method is very similar to rationalising the denominator at GCSE. We multiply both the numerator and the denominator by the conjugate of the denominator. So my denominator is 2 plus 4i, and I'll multiply that by 2 minus 4i, and multiply the numerator by the same. Then we multiply out and we get 2 minus 10i plus 12i squared, and difference of two squares at the bottom, 4 minus 16i squared. So 12i squared is minus 12, 2 minus 12 is minus 10, minus 10i, all over 4 plus 16, which is 20, and we get minus a half i. Pause the video while you try out the method for yourself with this one. OK, we start by multiplying top and bottom by the conjugate of the bottom. That's 2 minus 9i. That gives us 6 minus 27 minus 10, 37i, plus 45i squared, all over 4 minus 81i squared. That's 6 minus 45 is minus 39, minus 37i, all over 85. That's the end of this second video. In the next section, we'll look at visualising complex numbers.